Hello everyone and welcome. My name is Naveen Kumar and today I will present an overview of the new features that have been added to Remcom's XFdtd, which is utilized to design a 60 GHz phased array antenna for a WiGig application. To start off with, I will provide you the overview of today's presentation. First, we will look into the design of a single antenna element that will be used as part of a 4-element array, and then we will use the superposition and the array optimization features of XF to arrive at the different beam states of this antenna array. And in the end, we will look into two result types called max hold and CDF of EIRP, which can give us an idea of how well an antenna array is performing. Nowadays, there is an increasing demand for high data rates, high quality video applications around the world. Data rates of 3G and 4G technology do not satisfy the current data rate requirements and is expected to grow even more in the upcoming future. With the abundant spectrum advantage over 6 GHz, millimeter wave applications like WiGig becomes key enabler in providing high data rates for industrial and communication sectors. The WiGig system operates in the unlicensed 60 GHz band of the radio spectrum, providing a speed of 7 gigabits per second. Due to their small wavelengths, WiGig utilizes antenna arrays along with beam steering to support such high data rate applications. It is therefore a mandatory requirement to design and assess advanced antenna arrays to support an ultra-high data rate application. Remcom's latest release of XFdtd greatly assists antenna engineers with the design of antennas for such applications with the superposition and array optimization, which expands the software's capability to streamline 5G device design and beam steering analysis. To demonstrate the capability of XFdtd, we have designed a 60 GHz antenna array from Tav Zhong's paper, which can be used for a WiGig application. Here we have a single antenna element, which is an aperture coupled patch antenna with a compact fan-shaped feeding network along with a vertical quasi-coaxial via transition designed and simulated in XFdtd. The antenna stack-up contains 3 laminates, 2 bond play layers along with 2 ground planes. The antenna element is realized on the top layer with parasitic elements to have a higher bandwidth, while the antenna feeding network and the quasi-coax via transition are routed from ground plane named M2 to layer M6. The metal layer M6 is also planned for the realization of power distribution networks and low-speed traces. The antenna and RFIC ground are connected together by numerous vias. First, a single element is designed and replicated into an array of 4 elements as shown in the figure. An FDTD simulation is performed on such a structure with each port individually excited while all the other 3 are terminated with a passive load to obtain the S parameters. The S parameters of this antenna array is shown to the right. The blue curve demonstrates the S11 of the antenna array. Looking at the S11 curve, we realize that the antenna element has a bandwidth of roughly around 8 GHz spanning from 56.5 to 64.5 GHz with a decent isolation between other ports. Next, we have the near field and the far field results of the same antenna pattern. In the top to the right of the slide, you can see 4 near field E-field patterns of the antenna with each port individually excited. And to the bottom, you can see the radiation pattern of each individual element obtained by exciting individual elements one at a time. An FDTD simulation can take anywhere between few minutes to a few hours to completely simulate the structure and provide us with the S parameters and the steady state results. One good thing about having the S parameters is that it can be combined using the superposition principle to quickly analyze port phase combinations with a single simulation. The workflow of the superposition is pretty much straightforward. Once this FDTD simulation is performed, we use the post-processing option, which provides the users an option to input the input power and the phase per each port as the input to combine the near field and the far field data in real time. So having understood the workflow of the superposition simulation, here we have performed a superposition simulation on the antenna array design. To the right, we can see the near field E-field distributions of the individual ports with different input power and phase excited to each of these ports combined. To the left, you can see the field distribution when a minus 90 degree offset is provided between each ports, and similarly when there is no phase shift is provided between the ports, the E-field distributions look as shown in the figure at the center of the slide. And finally, we have a third combination with 90 degree offset provided between each port of the antenna array. Similarly, we have the far field pattern also plotted for the same antenna array with different phase offsets provided with each of these ports. As you can see, with running a single FDTD simulation and combining that with the superposition feature, we now get a much highly directive radiation patterns from each of these antenna arrays. The next feature that we have available is the array optimization, which determines the set of port phases that maximize an array's EIRP in a specified direction. Some of the supported use cases for this application are phased arrays, an individual phased array used in any of the devices, or multiple phased arrays used in an application. Also, we can support or analyze dual polarized antenna arrays, and also perform analysis on subarrays wherein separate elements or sub-elements of a bigger array can be analyzed as a group using the array optimization feature. The workflow for the array optimization is very much similar to the superposition feature, wherein we create an FDTD simulation, and with the results available, we then provide the input directions theta and phi along with all the allowable phases as the input to create an array optimization, at the end of which we can get the array optimization results. Here we have the array optimization performed on the same antenna array with different input directions provided as the input to the post-processing tool. In the first case, we have a theta of 30 degree and phi of 90 degree provided as the input, to which we obtain a directional pattern along with which the port phases of individual ports are available as the output, which can be accessed through the results part of the software. And similarly, we have two other beam that are actually generated for different directions for which the individual port phases are available as the output of the optimization. We are now at a point where we can actually compare the workflow of these two features. First one starting the superposition, wherein in this case we know the power and phase that is being given to each of the ports. Whereas in case of array optimization, we are not aware of the power and phase that would be getting into the uh, each antenna elements. So in this case, we provide the input directions and all the set of allowable phases as the input to the post-processing software. The last part of this presentation is to discuss the result types max-hold and CDF of EIRP. So these two are the result types that are available as part of the array optimization. And here in this case, we have 4-element array which supports 5 different beams ranging from -30° to +30°. And max hold pattern for such beam combinations is an envelope of all the 5 beams together. CDF of max hold is a single metric that allows users to look at the antenna design and figure out how well the array is performing and over how many angles it can cover with adequate gain. Here we have the CDF of first 5 antenna patterns. In this case, creating a CDF of these patterns would generate roughly the same pattern as shown in the right. The blue lines are showing the CDF of individual patterns here. So you can see that each of these patterns relatively have the same gain and same coverage per beam, and that's why all of these CDFs overlay on each other. However, since all of them are pointing at different directions, taking max hold of the same will include the effect of all the 5 patterns, and a CDF of such a pattern is shown in a red line on the graph here. And as you can see, to better understand this, if we have a 23 dB milliwatts of power input on an antenna, on the antenna, this would roughly provide positive gain for around 51% of the angles, and this is how we can evaluate the array performance. With this, I want to wrap up the presentation. I would like to thank everyone for attending today's presentation. You can always email us or contact us if you have any questions regarding the content that you saw today. I hope you enjoyed it and have a great day.